Okay, let's talk about one of the biggest questions in tech right now. We're building these incredibly powerful AIs that can write code, access data, and use tools all on their own. The question is, how do we prove they're safe? Not just hope they are, not just test them a bunch, but actually mathematically prove it. We're going to dive into a framework called Certifiable AI Safety Theory, or CAST, that tries to do just that.
So here's the plan for this explainer. We're going to start with the core problem of AI safety, why this is so tricky. Then we'll break down what CAST is, this new safety blueprint. We'll look at how its safety gates actually work, which is super interesting. Then we'll see it in a high-stakes, real-world scenario and wrap up by understanding the huge shift this represents, going from a world of unbounded risk to one we can actually audit. All right, let's get right to the heart of it. The AIs we're talking about now are not just fancy chatbots. No, these are systems that can actually do things in the real world. They can use tools like code interpreters, connect to APIs, pull from databases, and this huge leap in capability is exactly what makes them so powerful, but also so darn unpredictable.
And that, of course, brings us to the one question that motivates this entire field. You know, it's one thing to have an AI that helps you analyze a spreadsheet. It's a whole other ballgame when that AI is managing a financial portfolio or running a critical scientific experiment. How can you be absolutely certain, with mathematical proof, that it won't ever cross a line you've forbidden?
You know, right now, most AI safety is what we call heuristic. Just think of them as guardrails on a highway. They're reactive. They're a best effort attempt to stop the AI after it's already started to veer off course. CAST is proposing something completely different. Certifiable safety. This is proactive. This isn't the guardrail on the side of the road. This is the mathematical blueprint for the road itself, designed from the ground up to make it impossible to swerve into danger.
So the bottom line is this really fundamental shift in mindset. We absolutely have to move from just hoping our incredibly complex systems behave themselves to a world where we can formally prove they operate within the boundaries we set. It's the difference between crossing your fingers and having an engineering guarantee. And hey, speaking of which, if you're enjoying this breakdown of these complex ideas, a quick click on that subscribe button really does help us make more explainers just like this one.
And this is where CAST comes into the picture. Really, you should think of it as a formal engineering discipline for AI safety. It's all about defining the rules of the game before the AI even makes its first move. So what is CAST? Officially, it's a mathematical framework, and it's built specifically for the safety of these modern, tool-using AI systems. The key here is that it's designed to work at two critical moments: at deployment time, which is before you even let the system go live, and at runtime, meaning it's continuously checking things while the system is operating. Now, this is the really clever part, the core idea of CAST. Instead of trying to check every single possible action an AI could take, which is a basically infinite list, CAST does something much smarter. It certifies the AI's proposed probability distribution of actions. So what does that mean? It's not just checking the one thing the AI will do. It's checking the entire menu of things it might do and the odds of each one. It's a way more powerful and, frankly, more manageable way to think about safety. So this safe operating zone has a technical name, the safe set. Just imagine this enormous space that contains every possible plan the AI could ever dream up. The safe set is a very clearly defined region you draw inside that space, and it has these specific mathematical properties. It's closed and convex. All that really means is that it's a solid, predictable shape. There are no holes, no weird gaps. And that's super important because it gives you a clear, unambiguous boundary. If the AI's whole cloud of possible plans fits neatly inside that shape, boom, it gets the green light. It's certified safe.
Okay, so how does this actually work in practice? Let's get into the mechanics of these CAST safety gates. And probably the easiest way to think about it is like a bouncer at the entrance to a really exclusive club.
And this diagram here visualizes that bouncer perfectly. That big green area, that's the safe set. That's the club. The red cross, that's an unsafe plan from the AI. It's trying to get in, but its name is not on the list. Now, the cascade doesn't just say no. It can do a couple of things. It can just reject it and fall back to a default safe action. Or, and this is the brilliant part, it can project that unsafe idea to the closest possible safe point. That's what you see with that blue arrow. It literally nudges the AI's plan just enough to get it back into compliance. By the way, if you're finding this deep dive useful, a quick subscribe lets us know you want more explainers on topics like this.
So let's just break that process down into 3 simple steps. The paper calls it the master equation. Step 1, the AI proposes a plan as a distribution of actions. Step 2, the monitor, our bouncer, checks it and certifies whether that plan is safely inside the club. Step 3, the system acts. It either lets the original plan go through, lets the repaired, nudged version go through, or it falls back to a default safe action, like just saying, sorry, I can't do that.
Okay, but wait a second. There's a massive challenge here, right? AI systems aren't static. They create these constant feedback loops. The output from one step becomes part of the input for the next step. This creates a data stream that's dependent and constantly adapting. And you know what? Traditional statistics, which usually assume that all your data points are independent, completely fall apart here. So how on earth do you monitor this reliably?
Well, to solve that exact feedback loop problem, CAST uses some pretty advanced math called E-processes, and this visual explains it perfectly. Think of it like a super sensitive smoke detector. The green line shows the system behaving safely. The signal stays low, the alarm is quiet. But the second the AI's behavior starts to drift into unsafe territory, that's the red and orange lines, that signal starts to grow exponentially. Once it crosses a certain threshold, the alarm blares and the action gets blocked. It's a mathematically solid method that works continuously and doesn't get fooled by the system's own feedback.
All right, enough theory. Let's make this really concrete. Let's see how CAST could actually be applied in the real world, specifically in a situation that needs what the paper calls finance-grade containment.
So just imagine an AI. Its job is to predict stock prices. And to do that, it can write and run its own Python code to pull data, do analysis, make forecasts. The potential upside is massive, obviously. But the risks, they are absolutely astronomical. One mistake could lead to huge financial losses, maybe even destabilize a market. Now, with a framework like CAST, you can go way beyond vague instructions like "be careful." You can define and enforce very specific mathematical safety laws. For example, you could set a rule that the probability of the AI generating language that might be seen as market manipulation has to be less than, say, 0.01%. You could put a hard cap on a financial risk measure. You can make sure it never, ever violates trading policies. This means we could actually start to use AI in these high-stakes areas with a provable cap on the risk, which is just impossible with today's methods. But hey, safety isn't about just one single decision, right? A system can make 1,000 individually safe little choices that, when you add them all up, become incredibly risky. So CAST handles this with a concept called a global risk budget. Think of it like giving the AI a total allowance for uncertainty for the whole day. As the slide shows, you can even decide how to spend that budget. You can spread it out evenly or use more of it when the market is volatile. But the key is, the total accumulated risk can never go over that pre-approved budget. And all of this brings us to the bigger picture. Look, CAST isn't magic. It represents a very specific set of trade-offs, and understanding those is key to seeing why it's so powerful. It's really about moving from a world of unknown, unbounded risk to one of quantified, auditable risk.
The paper talks about something called the verification trilemma. Basically, for any safety system, there are three things you want, but you can't have all of them at once. There's expressivity, which is the ability to define fuzzy, informal rules like "be helpful." There's completeness, which is proving the system is 100% safe against that rule. And there's decidability, which is just getting a fast, verifiable answer. CAST makes a very deliberate choice here. It gives up a bit of expressivity to gain decidability. It doesn't try to enforce vague rules. Instead, it focuses on giving us provable guarantees for very explicit, formally defined safety laws.
And that leads to this really powerful quote from the paper, which pretty much sums up the whole promise of CAST. Its goal is to convert unbounded tail risk into quantified, auditable residual risk. In other words, it takes that terrifying possibility of a truly catastrophic, unpredictable failure, and it transforms it into a manageable known quantity. You're trading scary unknown unknowns for manageable known knowns. You know exactly how much risk you're accepting, and you can prove it. So I'll just leave you with this question to mull over. If we can really move from just hoping our AI is safe to actually proving it is, what does that unlock? What new doors open in science, in medicine, in finance, when we have a mathematical blueprint for trust in our most powerful tools? Thanks so much for joining us for this deep dive into certifiable AI safety theory. If you found this valuable and you want to understand the other complex technologies that are shaping our world, please make sure you subscribe for our future breakdowns. We'll see you next time.